on what I'm doing here with this? Okay. Do the same sort of thing for first order and second order questions, actions. I'm going to leave that last slide there. I guess, are there? Okay, so we talked last time about the units on the rate constant and how if we have, once we've predicted a rate law, we can determine the units on the rate constant, but it's hard to just know what the units are going to be on the rate constant unless you know the rate law. The units of rate that we typically see are in moles per liter per second. Basically, it has to be concentration per time. We typically use moles per liter per second. But because we have these three integrated rate laws that are clearly defined in terms of their initial concentrations after some time, and the unit of time, we can actually determine the units on the rate constant here, and those will be consistent. So if we know the units for a rate constant that is associated with an integrated rate law, we can determine if the reaction is first order, second order, or zero order. So for instance, when we take our integrated rate laws, we can set everything equal to the rate constant. Okay, solve for the rate constant. And then what we can do is substitute in units. And from there we can do unit analysis to predict or to determine the units on the rate constant for these reactions, or these equations. So I'll do the first order one, and then I'll give you the units for second order and zero order, and I'll leave you to do those if you'd like. But so I've rearranged the equation for first order reaction, setting everything equal to the rate constant. We have natural log of A at time t over a initial, or concentration initial, all divided by t. And so we can basically just plug in the units. So we'll have ln of moles per liter, because we're going to measure our concentration in moles per liter, over moles per liter, and all of that divided by time, which we'll put in seconds. Set that equal to the rate constant. Moles per liter divided by moles per liter, those units are going to cancel. And the only units we're left with now are inverse seconds. So the units on a first order reaction are going to be 1 over seconds. Units on the rate constant for a first order reaction is 1 over seconds. Make sense? Not fun, but makes sense? Okay, good. So for a second order reaction, you're going to end up with 1 over moles per liter, or inverse moles per liter, times inverse seconds, or 1 over m times s. And then for zero order, you're going to have moles per liter times inverse seconds, or moles per liter per second. So those are the units on the rate constant. I believe there's a question, at least one in the homework, that says, hey, these are the units on K, what order is the reaction? So that's how you do that. Okay. You could go through and do the unit analysis if you needed to, or you can put these to memory. Why couldn't I just say memorize? I think it feels bad. It feels bad to say that. Questions on that? Okay. So another cool thing we can do, this one's actually kind of neat. What we can do with integrated rate laws is determine the half-life for a given reaction. And this comes up when we're thinking about radiocarbon dating or nuclear chemistry. We can use half-lives to predict how long something will last. If it's a radioactive decay, we will get to nuclear chemistry way later in the semester, and we'll come back to these this half reaction for a first order reaction, or half-life for a first order reaction. Solving for half-life is relatively straightforward, and I want to show you how to do it because you can also then do this for more complicated types of things. So again, the half-life, what this refers to is the time required for a reactant to reach half its initial concentration. And we usually write it as T1 half. Okay? So we have an initial concentration of a reactant. That reactant reacts till half of its initial concentration. We figure out how long that took, and that's the half-life. So for a first order reaction, again we have this integrated rate law, which is the same as the one you saw previously, just written differently. You have to remember your rules for logs here to see this. The important thing here is this equation. What this equation is saying is that the concentration at time t is 1/2 the initial concentration, or A naught times 1/2. Okay? So it's 1/2 of the initial concentration. So using this, we can plug it into this equation, and that's what we do here. So we have natural log of A over T, or A sub T, which is A sub 0 over 2, that goes there, over A sub 0. We end up with natural log of 1/2, and that's equal to T1 half. The T1 half comes in because we're saying this is what the half-life is. So this is defining T as T1 half. Does that make sense? For every first order reaction, the half-life is equal to this value, 0.693 over the rate constant. That 0.693 comes from ln of 1/2. Okay, so if you're wondering where that's coming from, that's that value. So you're going to see that come up every time you do a half-life or first order reaction. So what this tells you for a first order reaction is that the half-life is only dependent on the rate constant. The initial concentration doesn't matter. We don't care what it was. We know how long it could take for whatever amount to decrease by half. And that's part of what we take advantage of when we do radiocarbon dating. For a second order, again, you could derive this. I will not. You're welcome. T1 half is equal to 1 over the rate constant times the initial concentration. So this one's dependent on the initial concentration. It's inversely dependent on that. Okay. And for a zero order reaction, T1 half equals the initial concentration over 2 times the rate constant. I can't remember if your book goes through deriving each of these, but again, you just plug in A at time t equals 1/2 A naught, and you can solve for this half. Make sense? I believe you're given, yes, you are given these equations for the exam. I don't remember if they explicitly say this is for first order, second order, zero order. So So check that. Okay, so let's do some examples here. So this is a reaction of N2O5 reacting to form NO2 and O2. This reaction is studied at 25 degrees Celsius, and we record the concentration of N2O5 at several times and obtain the data given in the table. How can we verify that this reaction is first order? And this is for a first order reaction. What do we do? Yeah. Yeah. We make a graph, natural log A time at time t versus time. And I've done that on the next slide for you. We can fit the data now to the equation for a line, y equals mx plus b. This r squared value is a correlation coefficient. When it is close to or equal to 1, that means it's a great fit to a straight line in this case. So here we have, we fit our data given in the table to when we've plotted natural log of the concentration versus time. And so that verifies that this is a first order reaction. If it didn't come out linear, if this was exponential or looked funny in some way, it wouldn't be a first order reaction. Okay? Only given the fact that this is fit to a linear curve, and the r squared here, you don't have to know r squared, but in this case that r squared verifies it is linear, says that it's first order. That make sense? Yeah. The values in the table. Oh, so I fit this data in Excel and came up with this equation just to verify for you. But I think, can't remember if I don't know if this is in your homework. I hope not. In any case, now we have this equation for the line. And so we know our slope, which means we know what? We know K. And we know the natural log of the initial concentration. We can actually verify by taking, what the hell is E called? E to the minus 2.3 to get 0.1. Can verify that we get this initial concentration back out. So you need that slope to figure out K. Okay. Let's do something that is probably more typical of what you'll see. All right, so let's calculate the concentration of N2O5 at 150 seconds after the start of the reaction. So we know it's first order. You can use our first order integrated rate law and calculate the concentration after 150 seconds. I'll let you do that real quick. You're going to need data from the previous slide. Are people getting 0, 3, 5, 6 most clear? Okay. So here I've written out how I solved this problem. We have natural log of the concentration at time t equals minus k times the time that we're interested in, 150 seconds, plus the natural log of that initial concentration. Yeah.
How are we supposed to do this without the y equals mx plus b equation? If you got the 0.0069, the equation in Excel.
Yeah.
Without that.
Yeah, without that you couldn't solve the problem. So you have to be given the rate constant at some point. Yeah. Alright, everyone okay with the algebra here? That natural log, what's E called? E to the, what's it called? You guys never remember. Just E. We take the inverse natural, what is it? It's not inverse natural log. Is it? I don't know. Is it an inverse? Yeah, E to the natural log, does that have a name? Yeah, right, yes.
Oh,
Yeah.
you're saying that
Like,
versus a-
yeah, is that, yeah, I'm saying that.
function.
Right. Yeah, they're the inverse. I just don't know if there's a particular name. I don't know what I'm thinking. That's what I'm Okay, questions on how to get to the answer? Other than my ridiculous one. Yeah. Yeah, so the question, will you be given the slope or the rate constant? Yeah, you're going to have to be able to get that, either get that value by some sort of calculation or you're given that value. Yeah. Some sort of calculation meaning you have a piece of data that allows you to get to that. But most likely I think that you're going to be given that rate constant in this type of problem. Other things? Okay. Calculate the half-life. Relatively straightforward here. We know our rate constant K, 0.0069. Plug that in. Calculating the rate life or the half-life for a first order is always relatively pleasant considering our options. And so we'll end up here with about, rounding here, 100 seconds. And so it's T1 half, first order, 0.693 divided by the rate constant. So that's how we get that. Okay, more challenging question now. How much time is required for the reaction to be 75% complete? We, in our integrated rate law equation, we're concerned about initial concentrations and concentrations after some time. If the reaction is 75% complete, how much is left? 25%. And that's what's important here for this type of question. So 25% is left. Okay? This is going to be, this question now becomes very similar to what we did with the half-life. So the concentration of A at time t is 1/4 or 0.25 of the initial concentration. Does that make sense? Okay. So from that, you can plug this into the integrated rate law and solve for time. And again, you need that K that we've calculated before. Okay. Want to work on it together? Let's do that. So I'm going to set everything equal to t. Did I write that correctly? Yes, I did. Oh boy, we get to really remember our rules for logs here, folks. Okay. So, rules for logs say if you are subtracting two things that you're taking the log of, that's equivalent to dividing them out. I didn't say that the way a mathematician would. All right, everyone okay with that? If you're adding them, you end up multiplying. Does that ring a bell to people? Okay, good. So I plugged in, once I've set everything equal to time t, I plugged in my A at time t equals 1/4 my initial concentration. A times 0 cancels out. I'm left with natural log of 1/4 divided by the rate constant k equals t, and I end up with 201 seconds. Questions on that? Yeah. Yeah, so the slope that we calculated was minus 0.0069, right? And we know that this slope is equal to minus k. So minus k equals minus 0.0069. Yeah. Okay. Yeah, you can solve this, and we know initial concentration. Is that what you used? Yeah, so we know initial concentration from our data table. So yeah, you could get away with not solving for doing the natural log and the rule of logs. You could plug in 0.1 for a sub 0, wherever that shows up, and solve for the answer. There's another way to do this problem. Has anyone come up with a third way? Yeah.
In this case, the third time down is literally 25% of the initial, so
Yeah.
you can just use the table.
You could use the table. Great. Yeah. There's a fourth way now. Okay, there's a fourth way. Yes.
Couldn't you just add the half-life of
Exactly. So here's an important thing to recall. How do I want to show this? Yeah, we'll do it linearly. Okay. So let's imagine we've got our integrated rate law plot for a first order reaction. We have our initial concentration. We'll just say it's 2, just to make our lives easy. Half-life is defined as when we get to half of that initial concentration, right? So we get to a concentration of 1. And so whatever this time would be T1 half. But we know from our half-life equation for first order integrated rate law, T1 half equals 0.693 over the rate constant. It's not dependent on the initial concentration. So from here, from our concentration of 1, we could find when the concentration is 0.15, or 0.5, excuse me. And that's going to be T1 half again, which is 1/4. That made sense in my head. But it's another half-life, okay? So if we're at, and maybe I picked 2 and 1 incorrectly. Let's see, if we're at 100% here, we are at 50% left here, and then we're at 25% left here. We go on, the next one, we're at 12.5%. Okay, so that will be 3 half-lives. And keep going down and down. So each one, because of the way that T1 half works for the first order rate law, you can just add up how many half-lives it takes to get to 75% remaining, or 75% complete, and add up that time. Does that make sense? So each one of these blocks is 100 seconds. It may not look like that on this plot, but it's supposed to be. And I'm enjoying your confused face. And I appreciate it. So T1 half, we've gone through half-life, now 50%, another half-life, drag out another 100 seconds, down to 25%. Does that make sense? Yes. Approximate. Yeah. Yes. Oh yes. The x is time, so that's linear. Concentration. Yeah, you're right. You're right. Let's just pretend it's right. Okay? Other things. It's hard to draw a natural log graph off the top of my head. Anything else? All right. Oh, good, we made it. Okay.